Hello everyone, I am Dr. Subhasish Saha, Assistant Professor in Physics, Department of HNS, MLR Institute of Technology, Hyderabad. So today is the sequential video of the quantum physics topic. So today I will discuss about these topics: Schrodinger time independent wave equation, particle in a box problem, physical significance of wave function, postulate of quantum mechanics, introduce the concept of operators in quantum mechanics, then what is eigenvalues, eigenfunction, expectation values. So first, what is Schrodinger time independent wave equation? As we know that it is a general expression of any plane progressive wave can be expressed psi equals to psi naught sine omega t minus kx or cos omega t minus kx, where this is the amplitude part, this is the phase part. So in this part, omega is the angular frequency which can be expressed by 2 pi f. It is a linear frequency. K is the wave vector which can be write 2 pi by lambda. So lambda is the de Broglie wavelength. Now suppose this expression can be differentiated with partially with respect to x. So we can write this expression del psi del x equals to minus k psi naught cos omega t minus kx. Again second time we differentiate with respect to x. Then we can write in this expression where this part is actually the wave function psi. So we can write in this expression. So this is the form. Now substitute this k equals to 2 pi by lambda and lambda equals to h by mv. That is the de Broglie wavelength expression. When you substitute these things, the general form will come into this form. Now we just little bit modified m square v square in terms of energy of that particle. We know the total energy equals to k plus v. K is the kinetic energy, v is the potential energy, and kinetic energy can be written as half mv square. So we can write in these things mv square equals to 2e minus v, where e is the total energy, v is the potential energy. Substitute this mv square into the previous equation. When you substitute these things, we can write in this form. And h can be substitute h by 2 pi equals to h cut. This is a reduced Planck constant. When you substitute all those things, the general expression will come del square psi del x square plus 2m e minus v by h cut square psi equals to 0. This is the time independent Schrodinger time independent wave equation. Now in case of 3D, instead of only del square del y square, there are two another coordinates will be added, that is y and z. So del x squared by del x square, del square psi by del y square plus del square psi by del z square plus 2m e minus v by h cut square equals to 0. So this is the Schrodinger wave equation where it is in 3-dimensional. Del square, capital del square is in this form. When you substitute these things, the general expression of Schrodinger time independent wave equation in 3D can be expressed in this term. Now we know what is the Schrodinger time independent wave equation. Now one of the very common problem is particle in one-dimensional box problem. Suppose we know that the electron is moved inside any matter or material, right? So those are treated as a wave. So those have some hard boundary is there. So like electron is trapped inside some metal or material. This means charge carriers are trapped by some potential barriers. Okay. For these type of problems, this can be approximated by an electron in an infinitely deep one-dimensional potential well. Okay. So how to solve this type of problem? Suppose there is a region x0 to L where the particle exists or electrons is moving. Particle is exist and those are moving inside this region. And there is some hard boundary wall at x equals to 0. That's why at x equals to 0, potential Vx equals to infinite. At x equals to L, Vl equals to infinite. So this means hard boundary wall is there. These are hard boundary wall, and so since the particle exists only in this region, so wave function will exist only in this region. Okay, and this region potential is 0. Particle can be freely move inside this region. Okay, outside of this region where x greater than L and x less than L, in these cases classically particles cannot be penetrated out. So in this region we can consider wave function is 0. Only in this region wave function not goes to 0. Okay, now to solve this type of problem for with the help of Schrodinger time independent wave equation, let's see. So this is a Schrodinger time independent wave equation. Inside the box region x less than L and greater than 0, in this region potential is 0, particle freely move. So we substitute v equals to 0, then we can write this one, where we can consider k square equals to 2m e by h cut square. We substitute these things, then it comes to like that form. The general expression of the above equation is psi x equals to a sin kx plus b cos kx. Now we apply the boundary conditions to determine these constant a and b. Okay, what are the condition? At x equals to 0, wave function goes to 0. At x equals to L, wave function goes to 0. First boundary condition we will apply. So at x equals to 0, wave function goes to 0 when you substitute all those things. Okay, so this is gives that v equals to 0. Okay, b equals to 0, this means the wave function will come psi of x equals to a sin kx. Now in this case we apply the second boundary conditions. Second boundary condition, x equals to L, at x equals to L, wave function goes to 0. We substitute those things. Okay, then it will come this form. Okay, now a can never goes to 0 because b is already goes to 0. B already goes to 0. If a goes to 0, then this part is always goes to 0. If b goes to 0 and again if a goes to 0, then psi is always 0. Then it is not actual reality. So what is the other things? A cannot goes to 0. It is not possible. Only the possibility is sin KL goes to 0. Sin KL goes to 0. If it goes to 0, we can write KL equals to n pi. So we can write k equals to n pi by L. So this is one thing. And last slide we got k square equals to 2me by h cut square. So we equate these two form. Okay, we equate those two form. So these are boundary condition. After supplying boundary conditions, the general expression is come this. Now we have to find this constant value a, that is called normalization constant. How to get these things? We know that particle is stuck within a region of space that x equals to 0 to L. So the probability of finding the particle within this region of space is 1, right? Within this region of space, probability of finding the particle is 1. So what is probability? Probability is like psi star psi dx equals to 1 in the region of 0 to L. So that is gives the total probability of finding the particle. So it gives a normalization condition. Okay, when you supply those things and substitute this psi value in this expression, we can calculate the constant value a equals to root 2 by L. So the general expression is this one, and n equals to 1, 2, 3 anything. When n equals to 1, it gives us ground state. When n equals to 2, it is first excited states. N equals to 3, it will give second excited states. What is the wave function form? When ground state is coming, at x equals to 0, wave function goes to 0. At x equals to L, wave function tends to 0. Okay, at x equals to L by 2 in this region, x equals to L by 2, the wave function, if you substitute L by x equals to L by 2, it's pi by 2, sin pi by 2, it's 1. So it's come root 2 by L. So that's why it is root 2 by L, this region, x equals to L by 2. Similarly, for psi 2, it's also there are at x equals to 0, one node is there. At x equals to L by 2, one node is there. At x equals to L, there is another node. So at x equals to, in this point, okay, this is called L by 4, x equals to L by 4, and this is x equals to 3L by 4. At these 2 points, if you substitute that in this form, okay, x equals to L by 4 and x equals to 3L by 4, it goes to root 2 by, it goes to 1. So that time it's come root 2 by L. So in this point, they have some peak. Similarly for psi 3, this is the ground state, first excited states and second excited states. What about the probability? Probability is the square of size. So that is the probability is coming. Okay, these are the probability amplitude distribution. Okay, so these are the, what is the nature of the wave function for ground state, first excited state and second excited states. Now come to the expression of energy. We already got k equals to n pi by L, right? In previous slide we got k equals to n pi by L, and k square equals to 2me by h square. When we equate these two form, we can get k square equals to, in these two form, when we equate this, we can easily get E equals to n square pi square h square by 2m L square. So this is the general expression of energy, okay, of any states, okay, for n En equals to proportional to E proportional to n square. This means, so this means energies are discrete, okay, it depends upon the n value. N is the number of states, ground state, excited states, okay. So E1 is the ground state energy, E2 is the first excited energy, so we can write En in terms of E1, right? Okay, that is the second excited state's energy. So this means it is proportional to n square. En is proportional to n square. So what is the energy plot? So it is the ground state energy E1, second excited state 4E1, third one is 9, then fourth one is 16. So it is proportional to n squared. So this means the energy levels are discrete. As we increase as we go for the excited states, the spacing between these two consecutive energy levels are also increased, right? It is not equispaced for particular box problem energy distribution. For 3-dimensional case, what is the wave function of nature? For 1D, there is only one part was there. For 3D case, along with x, y component and z component is also added. So the psi n in case of 3D, it is a product of three wave functions. So it is a product of three wave functions. This is for 3-dimensional case. In case of energy, when we come to the derivative expression, so earlier case on 1D only this term was there. Now two terms is added, this one and this one, corresponding to y coordinate and z coordinate in case of 3-dimensional case. So this is the expression En equals to nx square plus ny square plus nz square h square by 8ml square. This is the general expression for 3-dimensional box problem energy value. Now I will give the idea about the degeneracy. What is degeneracy? Look into this expression. There are three components, nx, ny, nz. Okay. So those are either 1, 1, 1 or how the configuration is there. For the ground state, those are only one configuration, 1, 1, 1. So corresponding to these are 3, this value. And energy value will come 3h square by 8ml square. So there is degeneracy is 1. Okay, now the question is, what is degeneracy? I will come. Next case, next possibility is 2, 1, 1 or 1, 2, 1 or 1, 1, 2. There are 3 configuration. For those cases, the energies have the same value. Okay, but how many configuration? There are 3 configuration. So this means degeneracy is number of linearly independent states, okay, having the same energy value gives the idea about degeneracy. So in this case, there is only one independent state is there. So degeneracy is 1, having the same value, same energy value. In this case, there are 3 configuration. All 3 configurations have the same energy value. Those are linearly independent states. So in this case, degeneracy is 3. Okay. So in this way, we can come to the degeneracy concept. Okay. Similarly, for 2, 2, 1, 1, 2, 2, 1, 2, 1, 1, 2 have 3 degeneracy. 2, 2, 2 is only one configuration. So it is non-degenerate states. These are degenerate states. In case of 1, 2, 3 has total 6 configuration. In those are linearly independent states because their wave functions are different. Okay. So that's why the linearly independent states are there, but the energy values are same. That's why degeneracy is 6. Now we come to the next topic, physical significance of wave function. What is, till now we discuss about Schrodinger wave equation, particle in a one-dimensional box problem. We discuss about the wave can be treated as a particle can be treated as a wave. Now what is the significance of this wave function? Actually the wave function has no direct physical significance. It is just a complex quantity. Okay. Representing the variation of matter waves. Now the probability psi star psi, basically mod psi square, is proportional to probability. It gives the probability of finding the particle at a particular point at a particular time. Okay, it has some meaning. It carry the information about the systems. Suppose the particle is belonging within a range x1 and x2. So probability is be x psi star psi dx x1 to x2. Within this region of x1 and x2, the probability of finding is the particle is can be written in this form. In case of 3D, there are three components will come, three coordinates x, y, z. Now suppose the particle is, we know that particles exist in a region, maybe that is an infinitely long region, then probability definitely will be 1. So in those cases, we can write integration minus infinity to plus infinity psi star psi dx equals to 1. Okay, this is also the normalization conditions. Okay, in case of 3D, three components will come. So these are the some significance. Okay, now the postulate of quantum mechanics we will discuss. So what are the postulate of quantum mechanics? First of all, till now we have discussed about the wave functions. Okay, it is actually give the state of a quantum systems. Okay, it's carry the information about that system. The complete information about the quantum system can be given or can be contained in a wave function psi rt or psi xt, 1D or 3D. Now we can find the probability of the particle within a region of space or region of volume d tau at time t, that can be expressed in terms of mod of psi square. Okay, this wave function must be finite, single valued, continuous, well-behaved and square integrable. Means this wave function will be continuous in every space. Okay, it has single valued, it will be integrable, square integrable. So that's why you can write integration mod of psi square d tau. Okay, so it is a square integrable, and if it is well behaved, mean it should be normalized. Okay, within a certain region of space. Okay, it should be normalized. Okay, it will give some value, so it will be some single valued. Okay, so these are the properties. Now we come to the discussion about observables and operators. What is observable and operators? Observable is any physical or dynamical observables like parameters, position, momentum, energy, those can be represented by a Hermitian operator. Those are any dynamical observables can be represented by Hermitian operator. So like position is can be written, it's a position operator x, momentum operator px equals to minus h cat del psi del x. Energy can be, total energy is a Hamiltonian. It is the part of two parts. One is kinetic energy, another is potential energy. Okay, that is also operator. Now question is, what is Hermitian operator? Hermitian operator has some property. One of the property is, suppose it should be right in this way, Hermitian operator. Suppose A is a Hermitian operator. A is a Hermitian operator. What are the properties can be right? There are, suppose two function is there, psi1. Suppose there are two functions, psi1 and psi2. Okay, and A is a Hermitian operator. So what is the Hermitian operator property? Hermitian operator property tells, suppose it is integration minus infinity plus infinity. Suppose there is a psi1 star, A is a Hermitian operator, psi2. Okay, it is one dimensional dx. It can be right minus infinity plus infinity. Okay, then A star psi1 star psi2 dx. This is the Hermitian operator properties. There are two. Suppose psi1 psi2 are the eigenfunction of this operator A. A is a Hermitian operator. So it is one of the basic definition of Hermitian operator. Okay, so all the operators are Hermitian operator. So if we take these things in case of momentum, if we substitute here minus h cat del psi del x, we will get this condition. It will follow this condition. So it is one of the Hermitian operator. Total energy is also Hermitian. Position is Hermitian. So all those operators are Hermitian operator. Now another property of Hermitian operator is the eigenvalue of any Hermitian operators are real, or the expectation value of any Hermitian operators are real. When this is valid, when these psi1 and psi2 are well behaved, means those two are normalized wave function. Psi1 and psi2, if it is normalized, if it is normalized wave function, then it will be satisfy this expression or this equation. Okay, these are the condition of Hermitian operator. This is one of the definition of Hermitian operator. And eigenvalue of any Hermitian operators will be real value. Expectation value is also real. Okay, now the question is, I will come to that in details. What is eigenvalue, what is eigenfunction? I will come to that point. So suppose what is eigenvalue, let's discuss about those. Eigenvalue is, suppose any operator, A is operator, okay, any operator operate on any function psi, it gives some value, it gives some another function, okay, it gives some another function. Okay, now if this function and this function is same, then it is called psi is the eigenfunction of A, and it will come some value, that is eigenvalue. Let's say example, suppose A is del psi dx and psi is sin x. If we substitute all those things, what is the outcome will come? D psi dx sin x. Okay, it will give cos x. So this means this function and what is the output is coming, those are different. So in this case, A is not like it is, psi is not the eigenfunction of operator A. Okay, now make it, suppose A is second case, this is case 1. Second case, suppose A is d2 psi dx square. Suppose in second case, suppose d2 psi dx square I take sin x, so it is cos, again it will come minus sin x, right? Because it will derivative 2 times, sin x will goes to cos x, again second time derivative it will come sin x along with minus. So in this case we note this is the operator A wave function is psi sin x, okay, it gives some value minus 1 along with the same wave function. Okay, so this means this is the this sin x is now this sin x. In this case, this sin x is the eigenfunction of this operator having some value, that is called eigenvalue. If the operator operate on a wave function, give the same wave function along with some value, then this wave function is called eigen wave function of this operator, and this value is called eigenvalue of that operator. Okay, so this is the some points. What is Hermitian operator? What is eigenvalue? What is eigen operator eigenfunctions? Okay. Now another possibility is, suppose any observables, okay, is measured. The only possible result is our eigenvalues. I already discussed what is eigenvalues. Suppose A is an operator, operate on any eigenfunction. Okay, it gives some eigenvalue along with the same. If it comes with the same function, then this is called eigenfunction of this operator. Will come with some value. That value is called eigenvalue. Expectation value is also can be expressed in this form. This is the expectation value. Suppose this is a wave function and it's operate on these things. So expectation value can be written in this form. Suppose A is the operator, okay, operate on the wave function, it gives some value A and psi. Okay, now substitute in this expression, expectation value is integration psi star e cap psi, okay, suppose dx. Okay, so A psi it gives you so A will come outside, integration psi star psi dx. Okay, it's suppose it is a region of space minus infinity to plus infinity. Within this region, this will be goes to 1, normalization condition. So it will come, expectation value is come this one. Okay, so when this is possible, only this part goes to 1. This part goes to 1. Okay, then only, so it is satisfy the normalization conditions, okay, then only this expression will come to give some value, eigenvalue or expectation value. So these are some property of or postulate of quantum mechanics. Another is probability of finding the particle. Suppose any, we are measuring on observable in a state psi. Psi is, suppose it is a linear combination of eigenstates, okay, suppose an phi n, n is suppose 1 to infinity, okay. So in this case, suppose you want to find the particle in a one of the states, suppose in phi n states. How can we write? So we can write these things. Suppose you want to find the, what is the probability of finding the particle in nth state? How can we write? We can write in these things, probability is like, it is one of the state and it is the total superposition states, okay. So this is the probability of finding the particle in nth state, okay. It should be, we can find it, and when it is possible, when psi star psi means basically it goes to 1, it's satisfy the normalization condition, then only we can write these things. So we can write, suppose it is a1 psi 1, a2 psi 2, a3 psi 3, dot dot dot. So suppose you want to find the particle in any one of the states, suppose it is psi 2 or psi 3, so you can find it in this way, okay. And the time evolution of the system, so it is basically, we know that the Schrodinger equations is can be written as h psi equals to e psi, right. So E can be expressed in terms of operator form, then we can write it h psi equals to, h can be written as I h cut del del t, okay. That E is an operator, suppose E energy can be written as I h cut del del t. So there is a, it gives a time evolution of Schrodinger equation, basically time dependent Schrodinger equation case we can write these things. So there are some postulates about the quantum mechanics, okay. So today I will stop it here. In next video I will come with some discussion about what are the application of this quantum mechanics, okay. So thank you.